Point of Module 1. Fill in a lot of stuff. See the highlighted items. Those are the items that I'm more interested in you being familiar with. You can find them in the textbook most of the time because they're either underlined or highlighted. So this is on energy, heat, and temperature. And we're going to try to get about half the notes done today. And I think we'll be okay to do that. Let's just jump right in, and we do have a few things for you to fill out. So, in terms of energy, you see the definition on page 37. We're going to define it this way. It's not what your mother accuses you not of having anything. Why are you laying around in bed all day long? You have no energy. No, that's not what we're talking about. We're talking about we are sort of, the ability to do work. You've got no energy to do work. You just lay around all day long. Energy is the ability to do work. Well, what work? Well, I want you to clean out the garage and clean up your room and clean out your closet. Well, no, that's not necessarily what we're talking about in chemistry either. And, work is the force, if you please write this down, the force applied to an object times the distance that object travels parallel to that force. Now the good news is that there's no equation here for you to learn. There's just a definition. There's just something for you to become familiar with respect to what work is. Why don't you do any work around here? Because, Mom, that's not what the definition here is in terms of chemistry. It's the force applied to an object times the distance that the object travels parallel to that force. So if I come here and there's the chair, all right, and I push on that chair. Oh, well, that's heavier than I thought. Here we go. I'll push a little harder. All right, I'm actually doing work because I'm applying a force to this chair and it is moving parallel to the direction that I'm pushing it. So in chemistry, that's the way we're going to define. I've applied energy, incidentally, to doing this work, which is moving this chair closer and closer to you guys, and it's becoming awkward. But anyway, so that is energy and that is work. But let's say I come over here and with all of my incredible strength, I go, I'm trying to move the wall. All right. What did I accomplish? Absolutely nothing. All right. So even though I might have expended, in terms of my own physical expression, some energy, I actually didn't in terms of the way we are going to define it for chemistry, because I didn't move the wall at all. All right. So no work was accomplished by virtue of my moving that wall. I did perform work moving that chair, but not the wall. All right, and I've got that right there in your handy dandy notes. Push against the wall with all your might, but it doesn't move. You've done no work. Okay. So how could we define it then? Energy is essentially the ability to cause motion. All right, in some way, shape, or form, and we are going to see that energy is not just the moving of pistons in your car such that it goes up and down and moves a motor. I never did understand about motors, but anyway, is able to move you down the road. We'll see that in terms of the motion of very, very small things like electrons, we see that energy is required to do that, and energy involved in the movement of those electrons. All right, let's define heat, if you would. Turn over to the next page, page 38. So there it is at the top. Heat is the energy that is transformed as a consequence of energy differences. You know what? I forgot to ask you here. So, sorry about that. So what do we have? How many mils? What do we have? Speak up. How many milliliters in here? Nobody got the answer, is that right? How many? Did you see it? You didn't see it. There you go. How many mils are in there?
I was just trying to find the curve of the one.
Pardon?
I kind of forgot to take the measurements. I was just
The meniscus at the bottom, yes. Did you see that though? It's very slight, you know, it just very, very slight, you know, in terms of maybe not even a full mil, maybe a half mil in height in terms of that meniscus. But the way you measure in anything, it works that way in beakers as well. You know, the little round deals. You look at that from the side. It works this way in any volume situation in terms of a liquid. You measure at the bottom of whatever that crescent is. In this case, I got 38 milliliters. That's what everybody else got. Thanks for speaking up. But you get the idea, right? In terms of it, you measure at the bottom of the crescent. That's called the meniscus. Might be something you'll be asked. All right. Anybody not get that? Anybody not understand? We're good? Okay. Simple stuff. I just wanted you to see it, and I forgot to bring it last week. Okay, so heat is the energy that is transferred as a consequence of temperature differences. And so in terms of it, what I want you to know is simply that definition. To become familiar with it, you will see that we will build on that as we go through the course. But for now, I just want you to be familiar with that definition in terms of the way we will use heat. In chemistry, it's the energy that is transferred as a consequence of temperature differences. Here's a couple of true statements that I've added for you in your notes. Heat always travels from hot to cold. If there is no difference in temperature, there is no heat. So if the temperature stays 99 degrees outside all day long, you can look me in the eye and say, you know what, there's no heat out here. And I'll say, yeah, you're right. If there's no temperature difference for the sake of chemistry, then there is no heat. All right, interesting statement. Again, contrary sort of to the way we live, but that's what we're going to do in terms of chemistry. Energy is trapped or stored in objects like wood that cannot be transferred until it is burned, and we're going to discuss that, well, in just a couple of minutes, as a matter of fact. Let's talk quickly about a hypothesis. So just write, a hypothesis is an educated guess, all right? The hypothesis, I better not, for the sake of time. We'll get there. We're gonna discuss climate change. We're gonna talk about that. We're gonna hit it, and if you, in terms of our conversations, I'll be glad to field your questions, and we'll go from there. But we got to talk about climate change before you get out of this course and begin to hear other stuff along the way. So, with regards to what I mentioned to you earlier on, something as simple as having a brain freeze on grams times grams, which is grams squared last week. That's an example of the fact that people get it wrong. And they get it wrong about big things sometimes, very big things. And in my opinion, they've gotten it terribly wrong with respect to this whole issue of climate change. The whole issue with regards to who and what is causing climate change. There's no question that the climate changes. Of course it does. There's evidence for that everywhere. The huge question for us these days is it changing, number one, and number two, what is causing the change? And of course, there is a political component now that is driving a lot of science, and sadly that political component is saying that humans and human activity is the main cause of climate change. And we'll talk about it, all right? But for now, the hypothesis is that human beings are causing the climate to change, all right? It's an idea. It's just something that you throw out and you think that's what the case is. Well, how do you prove it or disprove it? You elevate it to a theory, and the theory is more rigorous experimentation. So just put down a hypothesis that is confirmed by more rigorous experimentation. That's a lot of big words, but that's a pretty good definition of theory. All right? A hypothesis that is confirmed by more rigorous experimentation. So the scientific model says it's true if you can demonstrate it in a lab and repeat that. All right? That's the scientific model. If you can show that something works in a certain way, and then show it again and again and again over time in different places and different circumstances, all right? And so that is a theory. And scientific law says that if you're able to do that often enough and across time, after perhaps centuries of investigation with respect to a theory, then it becomes a scientific law. All right? Another bugaboo of mine is evolution, the theory of evolution. It is a theory, and has it been verified by rigorous scientific experimentation? I'd argue no. Contrary, and again, you're homeschoolers, so hopefully some of this stuff has already, you've come along to hear it. Some of you are right out of public school. Maybe you have been taught the theory of evolution as scientific law. In other words, as something that is so proven that we just know it as fact. And I'm here to tell you, it's just not true. I was taught that. I went to public school and I was taught that the theory of evolution is scientific law. And it really threw me for a loop in terms of my faith. You know, because at its roots, evolution it does not include a God. It simply is time plus chance, and in terms of the circumstances of the universe, and really threw me. And yet, what is the way to figure out whether or not a hypothesis is true? You check it out. And I checked it out. It took a long time and a lot of sweat. And I was grateful to have professors at the time at that fabulous Cal College on the Plains at Auburn who were Christians and were honest about evolution. In terms of some aspects of evolution is obvious, like selection. I mean, Darwin got that right. Of course selection is true. I mean, we do that with kitty cats. You like long-haired kitty cats, so you breed kitty cats in a certain way. You select for long hair in a kitty cat. You do that with beef cattle. You like great big beefy cattle, so you select certain whatever you call them, species of cattle, and you breed them and you produce, you know, big beefy cattle. It's with chickens, with anything else, and the same thing happens in nature. Selection is an obvious truth. But the fact that some primordial ooze could generate into the precursors of amino acids, and then amino acids, you know, energy plus time plus ooze, and it would result over billions of years in you and me. It's just not there. It takes much, much more faith to believe that than it does to believe the scriptures. So, and the scriptures are fairly easy to believe in terms of investigation. I have digressed, but I haven't. I've tried to flesh out for you the issues of hypothesis and theory and scientific law. Is there any questions about that stuff in terms of the definitions of them? Let's keep moving. So the first law of thermodynamics is this. I've written it for you. Energy cannot be created or destroyed. It can only change form. I would imagine you've been introduced to that at some point in time. So there is a certain amount of energy in the universe. It will always be it will always change form for the most part. All right? And we'll look at those changes in forms in some very basic ways in a second. God made only so much energy in the universe. Humans cannot create it or destroy it. When I was in college, we were told that we had 10 to 15, 20 years max of fossil fuel, of oil left to use. So we had to come up with alternative sources of energy, which incidentally I'm all for. I mean, wouldn't it be fantastic if something could ultimately happen with nuclear fusion, say. But anyway, 20 years, and we were done. And of course, as you see, there's more oil in the world and there's more discoveries every day than we ever would have dreamed of. I was in college in the 70s, late 70s, when I was told that. And, you know, there's more oil than you can shake a stick at, to say. But again, the purpose of that is to tell you that energy cannot be created and it cannot be destroyed. When we burn oil, we simply change the form of that energy that we were able to extract from the oil. Let's talk about potential energy and kinetic energy. If you would, turn over to page 40. There are the definitions. Potential energy is energy that is stored. All right, just write that down. Energy that is stored. Kinetic energy is energy that is in motion. So those two statements are actually things that we will look at a lot in this course. Remember what I told you. It's not cumulative, but we will revisit a lot of the concepts as we go through. And those are two. Potential energy is something that is stored. The textbook that you're turning through right this moment has potential energy in it. And some of you can't wait until the end of this course, or maybe you'll even break down in the middle of this course and try to determine how much kinetic energy has been stored in that textbook. You'll take it home and you'll put some gasoline or something on it and you'll add an energy source such as a lighter, and you'll burn that puppy, and you'll discover that there was lots of potential energy in that nasty textbook. All right? And that's the case for a piece of wood that you have sitting outside the house right now, because it's 1,000 degrees right now. But come the wintertime, and you'd like to have a nice fire, you'll bring that piece of wood inside along with some others, and again, you'll add some form of energy source to that potential energy that's sitting there in that piece of wood, and suddenly you're going to realize that there was a lot of energy in that piece of wood, and you're going to be nice and toasty as a result of that wood burning. And you will see, and incidentally some of these things can be measured, and we will do that, but you'll see that in terms of potential energy, there was an amount stored in that piece of wood, and then when you added some form of energy source to get the chemical reactions going, it's called a combustion reaction, incidentally, and to get the combustion reaction for that carbon-based piece of wood, somebody's at the door. So you will find out just how much kinetic energy was there. Questions about that, the difference between potential and kinetic energy. Heat is considered kinetic energy, as I've just sort of laid out for you in terms of the burning piece of wood. Questions about that stuff? Yes, sir.
Why is it called kinetic? What does kinetic mean?
I don't know, so we'll look that one up. The specific definition of kinetic probably has to do with motion. Kinetics, is that not motion? Somebody know that? You've got the eternal source of information. Somebody want to look that up? Look up the definition of the word kinetic for me, would you? Thank you. And thank you for the question. I don't know, but we're fixing to find out. Which is another, thank you very much for that too. And thank me for not knowing. Because
kinetic energy is what your body possesses by virtue of being in motion. So yes.
In motion. So kinetic means motion. I thought that's the case. So that's the origin of that word. But the reminder, so there sitting in your pocket is the source of all knowledge. You are the font of all knowledge, thanks to your Galaxy or your iPhone or your OnePlus, whatever you might happen to have. But it's the truth. You have at your fingertips a fabulous, fabulous source of information that, you know, up until these last, 20 years, really, I mean, in terms of really being able to use the internet on a phone, this is just fabulous for you. So if you have questions like that, it's just a look up away. And I heartily recommend you do that for this course and anything else. But thank you for the question. Thank you. Let's see how much more I don't know. There's lots. All right. A jewel is not necessarily something that you want your boyfriend to give you. All right? It could be. But that's a different jewel. This is a J-O-U-E-L. And as it turns out, it is a energy unit in the metric system. So if you just write that down. Metric system unit for measuring energy. All right? James Prescott Joule, he was a Christian. Neat story about him. But that's what a joule is. The metric system unit for measuring energy. So a joule is the equivalent of lifting 102 grams. So about how much is a gram? A housefly. So if you capture 102 houseflies, and they're everywhere right now, and you raise that straight up at a constant speed for 1 meter, you have used 1 joule of energy. All right? Got that for you there in your notes. Yes, sir?
Is there an English unit?
Pardon?
Is there an English unit for measurement?
Yes, and we're going to discuss several different units in just a little bit. But thank you. Yes?
I have a question back about kinetic and potential energy.
Okay, sure.
But, well,
Thank you. That's better.
okay, so can you have potential energy and kinetic energy like, at the same time?
Absolutely. Think of the burning log. Great question. Great question. But think of the burning log. You have, you know, whatever stage, as long as you've got log left and you see flame, you have both going on. You have kinetic energy being released in the form of heat. That's what's warming you up. And you still have potential energy in the form of whatever that log is that's left.
Is there a way to like measure the amount of kinetic energy, like the percent of kinetic energy versus the percent of potential energy?
Yes.
that you have?
Yes, and we're going to talk energy. I don't know if it's this semester or next, but yeah, we'll do that stuff. Great questions. Thank you. I can't believe it. And another question. Yes, sir. Got to talk loud from back there.
Is there a specific reason that it's 102 grams, or is that just an arbitrary number?
You got to say that again. Maybe no mask, too.
In joules, it's
Uh-huh.
102 grams.
Yes.
Why is it 102?
Why that?
Yeah. Is there a reason?
I don't know. We'll have to go back in time and ask Mr. Joule. But that is what the amount of energy is in terms of, and I think that's really more of an example. It was an amount of energy that he determined to be whatever it was at that time. And so one way to relate to that amount of energy is to lift 102 grams, 102 houseflies, a meter in distance straight up. All right. But that's a good question too. Yeah. Thank you. Anything else? Good stuff, guys. Thank you. Thank you. All right. So, statements at the bottom. Potential energy is difficult to measure. All right. However, kinetic energy is easy to measure in the form of heat and temperature. We will incidentally discuss measuring potential energy. It's not easy, but we will discuss it. Temperature and heat are not the same. They are related to one another, however. Temperature is measured indirectly by measuring the expansion of a substance. If you would, turn over on page 42. So I've had a thermometer, I was going to bring it, but I don't think I need to. Everybody's seen a thermometer, and there's a picture of one right there in your textbook, okay? There's the thermometer. So how is a thermometer measuring temperature, is measuring heat, all right? It's measuring temperature / heat by virtue of how much that substance inside the little tube goes up. Now, in terms of digital thermometers, in terms of the infrared ones, just don't ask me, because I didn't look that up. I'll have to do that before next time. Because again, the classic way and the way that we are discussing it in chemistry has to do with measuring the expansion or the reduction, in this instance, in terms of temperature, in the movement of a liquid. And so for years, mercury was used in those little glass tubes, and other substances have been used recently. But the bottom line to it is the way that temperature is measured for our purposes in this course is the movement of a liquid up and down in a tube. All right? Yes, sir. Which is, again, the equivalent of the expansion or the contraction of that liquid. Yes, sir.
Did they use mercury in the thermometers they would stick in your mouth?
What's that?
Did they use mercury in the thermometers you would stick in your
Oh, absolutely. And one of the coolest things in the world used to be to break them things and then, move that mercury around. Of course, sort of poison yourself while you're doing it, but that was sure fun when I was a kid. Absolutely.
You're not dead yet.
Say what?
So you're not dead yet.
Yeah, but that's kind of why I am, today. All right, I'm going slower than I wanted to go. We're not actually going to get as far as I wanted. Turn over, if you would, to, well, we're still there. Fahrenheit and Celsius were defined on page 41. Just wanted you to see. So, in terms of Celsius, that is I think they just define that as the metric unit for measuring temperature. Isn't that right? Let's see. It's not a very good description of it there. Let's look fast. Back to our handy dandy glossary. So, Fahrenheit, the temperature scale defined so that water freezes at 32 and boils at 212. All right, so that's fairly simple. And Celsius is, they do it the same way. I always thought of Celsius as being the metric scale. But again, water freezes at 32 degrees Fahrenheit and boils at 212. And Celsius, it freezes at 0 and boils at 100. And Kelvin is an important temperature scale which we will use increasingly so as the course goes on. If I can find that thing fast, I'd like to show you, and if not, I will show you for next week in terms of. So Kelvin is simply defined by Celsius plus 273, isn't that right? 273.15 degrees. So the way that you find Kelvin is just add whatever you have in Celsius to 273. And Kelvin is described as an absolute temperature scale because in terms of it, I should have looked this up first. There's a nice little graph that we will discuss when we get there. And it shows you, and I'll have to get it for next time. But the bottom line is draw it fast. So, all right, if you're freezing, let's see here, minus 270, 3.15. Everything known to man. Everything known to man. If you're dropping the temperature, if this is temperature, and you're dropping the temperature in terms of volume, Okay? Everything known to man decreases on a straight line towards 273.15 degrees. All right? Everything. Whatever compound you can name, it heads in a direction to 273.15 degrees on a straight line. It's the most interesting thing, isn't it? And as a result of that, the fact that everything we know that you can continue to cool down, and of course what's happening when you're cooling something, if you can remember, the molecules are slowing down. They're hardly moving, right? And in terms of volume, as a result, as you cool something, the volume is getting smaller and smaller and smaller. And to the point where all of these lines are heading to minus 273.15 degrees. Well, can you ever get to 275.13 degrees? 273, sorry. Can you ever get there? No. And why couldn't you ever get there? Because, you want to tell me?
Because there's always some little spark of energy.
Of course, you can't destroy or create matter as well as you can't create or destroy energy. And so if you got to zero volume, you wouldn't have anything anymore, right? Well, you're never going to get there. But everything in the universe heads to 273 degrees centigrade. And of all things, we got to quit. So let me give you your tests. And we'll pick this stuff up next week and finish out that stuff. But don't go till I get you a test.